All right, let's read through this problem here. Okay, let f be a function that is twice differentiable. So we know that means we have a smooth curve here. Okay, for all real numbers, the table above gives the values of f for selected points on the closed interval from 2 to 13. Estimate f prime of 4. And we don't have a function f of x to find the derivative, so the next best thing is to just find the what? Slope. Yeah, slope is just the algebraic version of calculus, and we can't find the exact slope, but we can estimate the slope. Which points would you use to find the slope here? Yeah, choose the closest points to your target, right? Between 4 is close, 3 and 5 is the closest x values to 4, so we'll use those 2 points. And use squiggly line to indicate that it's just an estimation. And then you just do change in y over the change in x. -3. Okay, part B, evaluate the definite integral of this function. Show the work that leads to your answer. Now, there's multiple parts here. Anytime there's a plus or minus separating your terms, and there's nothing outside the parentheses, so we don't have to keep these together. I think let's just make things easier if we separate this into smaller problems, because there's 2 things that's going on here, and it's easier to just go ahead and think of it as 2 separate problems. Okay, let's do that. What if I thought of it in this perspective? Integral of 3 dx minus, and I can pull the 5 out in front. Now, there are 2 distinct ways that we're going to approach each integral. What rule do you think we're going to approach for the first one? What's the integral of 3 dx? What rule do we use there? Any idea? No? Okay, so this is going to be power rule. Right? What is 3 going to turn into? What's the integral of 3? 3x, yeah. So we'll do power rule here, and then we can plug in upper and lower bound. But this is f prime. This is in function notation. So what's f prime going to turn into if we make it go through an integral process? Yeah, f. So this is applying first theorem here. So this is function notation, and this is power rule. So we have 2 distinct ways of going through. This is the specific rule we have to use, and this is more of a concept that we can apply, right? F prime becomes f of x. Okay, so we'll apply them separately. We know 3 becomes 3x. Go through power rule here. And after we go through power rule, then we are ready to involve the bounds. Yeah, so 39 minus 6. We can handle this as well. We know that f prime will turn into f of x. And once we apply the calculus of this problem, we can work in the bounds. And where can I pull to find f of 13 and f of 2? Yeah, from the table, right? F of 13 is 6, and f of 2 is 1. So now we can do the result of these two, right? 33 minus 25. Okay, questions there? Right, part C, yes, use left Riemann sum with all the subintervals that we can that's provided in the data to approximate the definite integral from 2 to 13 of f of x dx. Show the work that leads to your answer. Okay, so we'll go to our table. We'll block off each of our subintervals there, and then we can subtract the x's to get the width. Right? So 3 minus 2, 5 minus 3, 8 minus 5, 13 minus 8. So the numbers here, those are the widths we're going to use, and the heights will come from the f of x. So left Riemann sum, the first rectangle will be 1 times 1. Second rectangle, 2 times 4, 3 times -2, and 5 times 3. Okay, any questions there? Okay, part D requires a bit more space. I'm going to put this on a separate sheet here. Everybody good? A through C? Okay. All right, so here's part D. Suppose that f prime of 5 is equal to 3, and f double prime of x is less than 0 for all x on the closed interval from 5 to 8. Okay. Let's just go ahead and, just for our purposes, let's just verbalize what this means here. What does f prime of 5 equals 3? What does that mean graphically, visually? Good. So that means on the graph, yep, at x equals 5, the graph will have a slope of 3. Right? So we know the graph is going to be rising with a slope of 3. Whatever the graph looks like, or wherever the graph is, it's going to be rising at that point, a steepness of 3. Okay. Right. And let's visualize what this means. F double prime of x is less than 0. What does that mean visually? Concave down. It says everywhere, right? So the whole graph is concave down. Well, sorry, from 5 to 8. So if the graph has a slope of 3 and concave down, then we can kind of visualize how the graph is going to look, right? It's going to have this shape, right? And then at 5, it's going to have a steepness of 3. So at least we know how the graph is going to look like. We have some idea how the graph is going to look like at that point. From 5 on, it's going to be rising, but maintaining that concave down shape. Okay, so at least we have a visual understanding of our scenario here. Use the line tangent to the graph at x equals 5 to show that f of 7 is less than or equal to 4. Use the secant line for the graph to show that the graph f of 7 is greater than or equal to 4/3. Okay, so let me kind of talk about what we are trying to do here. What we're trying to do is this concept. Okay, the concept is if my graph is concave down, then any tangent line that I create, what's the relationship to a value on the tangent line to the curve? Is it going to, it's obviously not going to be exact, but is it going to over approximate or is it going to be under approximating? Over approximating. So any point that you find on the tangent line is going to sit above the graph, right? So the tangent line on the concave down graph is going to over approximate. Now a secant line is a line that goes between 2 points. Now, if you look at a secant line, is a secant line going to over approximate or under approximate an actual point on the curve? Under, right? It's going to sit below. Right? So that's the relationship that we're going to be targeting when we're going through this process. Okay. Now, the flip side, what if the graph was concave up? Then any tangent line that you create is going to sit what? Below the curve, right? It's going to be an under approximation. And any secant line that you create is going to be over approximating. Okay, so that's the big idea that we're going to be kind of building off of for part D. Okay, so I think it helps if we can kind of sketch this graph out just so we can have some just have, it doesn't have to be exact, but we can at least have something to work with here. So I'm gonna sketch a graph out. Okay, I plot all these ordered pairs here, 2, 1, okay, 3, 4, 5, -2, 8, 3, 13, 6. Okay, so we kind of sketched the graph, but as we sketch the graph, we don't want the graph to go right down and let that be the minimum, right? Because we know that at 5, there's going to be a slope of 3, and it's going to be concave down. So we probably want to have the graph look something more like this, where it's going to dip below, and it's going to have to come back up, because we know that at 5, there must be a slope of 3. So, and make the rest of the graph concave down, just so we can have some visual, right? Something that's consistent with the information that we've gathered. Right, so I've created something that looks like a slope of 3, or at least a positive slope, and then I'm making everything concave down after that. Okay, so what we're going to do is we're going to find the tangent line to the graph at x equals 5. So let's just create what the tangent line could look like, and then we're going to find the equation of that line. Okay, so let's do our tangent line here. It says find the tangent line at x equals 5. So we need to order pair. What's my order pair at 5? Yeah, 5, -2. And the slope is what? 3, right? Okay. Tangent line, let's do point slope form. Okay, I'm just going to rearrange here, at least make it a little bit cleaner. I'm going to move that 2 over to the other side. Okay, there's my tangent line. Now the problem says use the tangent line to show that f of 7 equals 4 or less than or equal to 4. Okay. Well, let's plug 7 into the tangent line and just see what we're working with, right? So what's the tangent line going to give us at 7? So 7 minus 5 is 2, 2 times 3 is 6, 6 minus 2 is 4. So our tangent line is giving us a y value of 4. So can we conclude that f of 7 is going to be less than 4? Yes, right, because we know the tangent line, if the tangent line is going to give us an over approximation, then we know our graph is going to be sitting below that y value. Okay, so we can use this as justification since f of x is concave down. The tangent line because the tangent line gives us a y value of 4, we know that f of 7 must be less than or equal to 4. Can't rise above that point. Okay. Now the second part says use the secant line between 5 and 8 to show that f of 7 is greater than or equal to 4/3. Okay, well, let's create that secant line equation first. Secant line equation is going to be the equation of this line between 5 and 8. It's going to be this line right here. Okay, so secant line, same thing. We're going to gather order pair and slope and then 2-point slope. But secant line, we got to use 2 points, right? So secant line is going to go through order pairs at 5 and 8. We know the order pairs at 5 and 8 will be 5, -2. We'll gather information for our secant line. Let's find the slope first. Change in y over change in x. It doesn't matter which point you choose. Either point will give you the same equation. So I'm just going to choose this one. Okay. Either way, all we need is point and slope to find our tangent line, or in this case, secant line equation. Okay, we'll start putting information in. Get y by itself. And now let's figure out what the secant line gives us, right? Let's plug 7 into the secant line and see what that gives us. 7 minus 5 is 2. 2 times 5/3 is 10/3. 10/3 minus 6/3 is 4/3. So we know our secant line is giving us a y value of 4/3, and we know the secant line is sitting below the curve. So we can guarantee that because the secant line sits below the curve, the graph is going to produce a value that must be at least greater than or equal to 4/3. So as you can see, you can kind of imagine how, as we go through more and more FRQs, that part D, or the last part of your FRQ, is usually significantly more challenging, right, than your A, B, C's. So that's how they typically design FRQ problems. They kind of start easy and they kind of build their way to more involvement. So, when you get to the AP exam, it's understandable that sometimes you may get stuck on part D, but don't let that stress you out. If you can get parts A, B, at least you can earn a few points from every part. If you can at least try part D, I think that's good, and you don't have to earn every point to be successful. So, but what you don't want to do is you don't want to get stuck on the last part and just keep looking at it and then neglect the other parts of your test and lose time that way. So, typically, if you can earn, every FRQ is worth 9 points. If you can earn 4 to 6 points per FRQ, I mean, you're on track to earn a 5 on AP exam. So it's possible that you can potentially skip every part D of FRQ and still earn a 5 on AP exam. Now, you don't want to, you at least want to try part D, but just saying that, typically in the past, the curve is going to be a little different every year, but typically anywhere around 63 to 65% on your AP exam is enough to earn a 5 on the AP exam. A 50% is typically a 4, and a 38% is typically a 3. So, now, they give that generous curve because the problems are typically not super easy. So every problem is going to be at least multiple steps to get to the answer. But at least that there's that generous curve that is supporting your efforts. Okay, let's look at page 6. Okay, so Ben rides a unicycle back and forth along a straight east-west track. The twice differentiable function. So again, we're dealing with a smooth curve. We know there's not going to be any sharp turns or any holes or asymptotes along this graph, along these graphs. Okay, measured in meters from the western end of the track. The table above gives values for B of t and Ben's velocity, V of t, measured in meters per second. And select the times t. And use the data in the table to approximate Ben's acceleration. So what's the relationship between acceleration and velocity here? Okay, acceleration is the what? Derivative, right? But we don't have a velocity function to find the derivative. So the next best thing is just involve what? Slope. Yep. So we'll just do the slope at 5. We'll pick the 2 closest points. So which order pairs do we want to use? Yeah, we'll do change in velocity over change in time between 0 and 10, right? 5 says between 0 and 10. It's not super accurate, but that's the best we can do here. Okay, squiggly line to indicate this is an approximation. Change in velocity divided by the change in time. Okay, using correct units, interpret the meaning of the definite integral from 0 to 60 of the absolute value of v of t. Right. So we saw this yesterday, right? What does this mean here? Absolute value of v of t, integral of absolute value of v of t gives us what? See at the top of the page. There you go, yeah. So without the absolute value, it'll be displacement, but with the absolute value, that means every forward and backward movement, we're identifying each as a positive, distance. Okay. So total distance in meters that bend rides in the 60-second interval. And then the second part is involving left Riemann sum, right? So left Riemann sum, we can go to the top of the table and involve v of t, right? The area under the v of t is going to give us the total distance. We're not going to use b of t, we're going to use v of t. Now, all the velocity is positive, so we don't have to convert any negatives to positives. We just use the values as we see. So width times height. The width is the distance between the seconds, the time intervals. And then the height, you're going to pull from your v of t row. Okay. Width times height, width times height, width times height. And we're choosing the left endpoint, left velocity value of each subinterval. Okay, part C. Between 40 and 60, must there be a time when Ben's velocity is 2 meters per second? Justify your answer. So I think our first instinct is just to look at the velocity, right? So between 40 and 60, just by looking at velocity, does it look like we can guarantee it? So this is not a good fit for IVT, right? So we definitely are not going to be able to use that, but maybe there's something else. Is there another way that we can approach it to maybe see if we can guarantee a velocity of 2? So how can B of t help us out here? What's the relationship between B of t and B of t? B of t is the, right, okay, B of t is velocity, is the what of B of t though? Derivative, right? Another word for derivative is slope, so maybe I can think of it as, can I guarantee a slope of 2? Right, if I'm trying to guarantee slope, then what theorem is that? That's not IVT, but that's what? Mean value theorem. All right, so maybe we can approach it from a mean value theorem perspective because they do give us that data. So why don't we find the slope between the endpoints? If it does give us 2, then we can guarantee that if there's a slope of 2 between the endpoints, there must be a slope of 2 somewhere along the curve. Okay, so we'll do change in meters over change in time. And we're going to see that it does give us 2. And so IVT was not a good fit for this problem, but because we have B of t, we have the original function, we can use slope to confirm that we can guarantee that velocity of 2. So by MVT, since B of t is continuous and differentiable, continuity with brackets, differentiable with parentheses, then there must be a time t where V of t is equal to 2 because we found that the change in position over change in time, the slope of the endpoints did give us 2. So if there is a velocity of 2 average velocity of 2 between the two endpoints, then there must be a specific velocity of 2 somewhere in that interval. Okay, let's look at 6D. says a light is directly above the western end of the track. Ben rides so that at time t, the distance L of t, the distance L of t between Ben and the light satisfies this equation. L of t squared is equal to 12 squared plus B of t squared. At what rate is the distance between Ben and the light changing at time t equals 40? So what are we trying to find based off this last question here? We're trying to find what? So what does that word rate indicate? Are we trying to find L of 40? It's going to be rate as derivative, right? So we're trying to find L prime of 40, right? So that means we got to find the derivative of this equation. But before we can find L prime of 40, we first have to find L prime of t. To define L prime of t, we have to go through our derivative process. Now, can you recognize a method we have to involve here if we want to find the derivative in this form? Chain, good. This outside, inside portion we got to jump through, right? Okay, so chain rule here. Okay, outside's derivative, that bracket squared becomes what? 2 bracket to the first power times what does inside's derivative become? L of t becomes L prime. And there's the, there's our L prime that we're going to be looking for, okay? Right side, what does a 12 squared become? Good, it's a constant, right? Goes 0. And same thing here, chain rule for B of t as well. All right, so we have L prime of t showing up. Let's replace every t with 40. And then let's see what information we can use from the problem to help us get these down to numeric values. Okay, so B of 40 we can find from the table. How can I find B prime of 40? Sorry. Yep, good. Yeah, B prime of 40, that's another word for velocity, right? So B prime of 40 is 2.5. B of 40 is 9, so that's good. We have 2 out of the 3 that we're looking for. How can I find L of 40? Good. I have my LT equation, right? So I'll insert into my LT equation to get L of 40. And then that will allow me to get numeric values out of these 3, and that I can isolate and solve for L prime of 40. Okay, so let's work on L of t. Let's find L of 40 here. B of 40 is 9. 9 squared is 81. $225, I can take the square roots. to get it down to L of 40, which is 15. Okay, so now I can insert into this and then get L prime of 40 by itself. Okay, B of 40 is 9. B prime of 40 is same thing as velocity at 40, right? B of 40. Okay, divide both sides by 30, and I can isolate L prime of 40 and get to my answer. Okay, any questions? All right, so your homework is pages 7 and 8. I'll send out a reminder this afternoon. If you didn't quite show me all the homework that was due as I was walking around, you can always send me photos of your homework that you want to show me to earn that 4 credit, or you can show me tomorrow for 4 out of 5 points. Make sure you send 1 picture per text. Okay. Well, you got to go through the calculus before the 13 and 2 function, right? 13 and 2 is the last thing you run, right? You got to do the indefinite integral before the bound gets involved. Thank you. Next test is chapter 5. Okay, thank you.